Okay, welcome to lesson 31. So for week 6, I think we're on week 6, right? It's kind of hard to tell. We're going to look at single factor ANOVA. So what we looked at a little bit last week was comparing the means of two groups. I hinted that we might go ahead and look at means of more than two groups, and that is what we are looking at this week. So single factor ANOVA. So when we want to compare more than two means, by all means you can use it to compare two, but it's equivalent to that two sample t-test if you only have two populations there. So ANOVA, where does that come from? This is the analysis of variance. So ANOVA. You might notice we use an R function called AOV, analysis of variance. So people call it different things, but ANOVA is short for analysis of variance. So when we want to compare more than two means, the example we're going to use for pretty much this chapter here, we have porous carbon materials. They're used for a lot of different things. Like absorption, electrochemistry, batteries, so on. But we have an experiment where we are going to take these materials and apply heat to them. Specifically, we have 4 different temperatures that we're going to use. And then we are going to measure 5 observations for each temperature. So I'm going to have 5 materials at 300 degrees Celsius, 5 at 400, 5 at 500, and 5 at 600. So I'll have a total of 20 observations. So from there, we'd be interested in looking at the following for this study. What are the factors? So what makes the groups different from each other? And this is going to be your treatment or your temperature. And then your treatment are going to be the levels of temperature. So if temperature is what makes them different, what different temperatures do we use? We'll have 300 degrees Celsius, 400 degrees Celsius, 500 degrees Celsius, and 600 degrees Celsius. These are my treatments here. My experimental units. So this is when I'm interested in what I'm actually analyzing here. These are the 20 carbon specimens. It's kind of peculiar to call them specimens, but that is what we have here. So the 20 carbon pieces that we're looking at. And then response. So the response variable, this is essentially getting at what do I measure from each of these 20 carbon specimens. So what we're looking at is the pore size. I do not know the units, otherwise I would include them, but I imagine it's fairly small. So looking here at this box plot, we might just preliminarily look, is there visual evidence that the treatment means differ? One of the big things that we look at is for overlapping or non-overlapping boxes. So if you look here, treatment at 600 degrees Celsius, its box doesn't overlap with any of the other 3 boxes. If you look at 500, it's kind of close to 600, kind of close to 400, but it's not as close to 300, and so on. Versus 300 and 400 degrees Celsius boxes, they look pretty similar. Yes, the medians are in different places, but there's a lot of overlap in the boxes. So this is just kind of preliminary. Like, I would probably argue that 300 and 400 are similar, but 600 and 300, those are not very similar. So comparing, so when we want to compare the means of 2 or more groups, what we do is we compare the averages between groups, so from group to group, as well as the variability within groups. So the mean squared treatment, I called it groups before. is going to be the average variability between groups. So you're looking at, oh, well, group 1 is how different from the overall average when you disregard groups. That kind of idea. We also, and you might definitely see in WebAssign, this equation here. The big caution, though, is this letter J. You want to use this like this in the instance that you have equal sample sizes across groups. So if you are lucky enough that you have the same sample size in every group, J is the sample size that's in all the groups. However, it can happen that you don't have equal sample sizes. That is very, very possible. And then we'll also look at the mean square errors. So this is how much is not honestly explained by the different groups. So this is the average variability within each group. So we look at the variability between the groups, how far apart are they, and then we look at the variability within them, how much variability is going on within each group. And here it's very, very handy legend for labeling all of these. So, and you might note, so this is saying, okay, well, this takes into account the sample size for everyone, and then this is this looks at the variability of each group. And then I is the capital letter I is the number of population or groups. J is going to be the number in each group as long as that number is the same in each group. X bar I, so this could be X bar 1, X bar 2. So for whichever group you're looking at, it's the sample mean for that particular group. If you see just X bar dot dot, that's saying this is the overall mean. So if I averaged all of the observations, regardless of whichever groups they're in, this is the overall mean, or we also call it the grand mean. SI is the standard deviation for that particular group. And then I use this N total, so the total combined sample size. Okay, so I'm visual, so I wanted to go ahead and visualize a little bit of what was on that last slide there. So what I did is, this is the same problem. We're still looking at pore size by treatment, by temperature treatment. So this black line here, this is X bar dot dot. This is the overall mean. So when I took all 20 observations in all 4 samples and averaged them, the average pore size, it was just a little under 7, whatever the units are. And then I did this same thing for, so this is the sample mean for the 600 degrees Celsius group. This is the sample mean for the 500, sample mean for the 400. I guess you could add dots here. And this is the sample mean for the 300. So what we are going to end up looking at is, if the means are the same for all of them, we could say that they are all equal to this overall mean, because knowing what group it is has no impact on what we think is happening with the means of the each treatment. However, what then we are going to investigate is, well, how far away did we observe each group mean from that overall mean? If they're very, very spread out from that overall mean, this might be a really good indicator that, hey, something is going on. Maybe at least one of these means is different than the others, that kind of thing. So we do investigate variability, like how far do they vary from that overall mean. But then we also have to account that how much does each group vary within itself. Because if they vary a lot, you're going to need to have a bigger distance from that overall mean. Okay, so now we're going to go ahead, take the sample data. This is all the data for that temperature and carbon pore size example. These are my 20 observations. This is the mean for each group. So at the 300 temperature, degree Celsius temperature, the average pore size was 7.45, and this was the variance of that sample. And you could look at it for each level there. So here I this is my number of groups. This is going to be 4. Conveniently here, we have the same number in every single sample here. So J, this is going to be 5. We have 5 observations for each temperature treatment. So then if I want to go ahead and calculate these, so MS treatment, I'm gonna make some space here, MS treatment. Do note that little r matters because later on we use like sum of squares treatment versus sum of squares total. You're going to want to make sure you include that little r. Otherwise it can get really confusing really fast. So it's going to equal, because Ni is equal to 5 for all groups, it's going to be, just a reminder, Ni times x bar I minus x bar dot dot squared over I minus 1. So what I'm saying is that's going to be 5 for all of them. This is going to be a constant 2. That's just going to be a 4 minus 1. So I'm going to get 5/3 times. So group 1, 7.45 minus. And that is one thing. We need to have the overall mean. So typically, how you would want to do that is you would add all 20 of these and divide by 20. Because you do have the same sample sizes in each treatment group, you could average these x bars. Just know that that will not work if you have unequal sample sizes. It will give you the wrong answer. So if you go ahead and you add up all the observations plus dot 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 all the way through point, divide by 20, we're going to get 6.9475. This is going to be my overall mean. So if I average all 20 of these. So here, 6.9475 squared plus mean of 400 degrees Celsius group, 7.28 minus the overall mean. By all means, feel free to pause, write this out yourself, check your answers. We encourage it. Minus 6.9475 squared plus 6.34 minus. There we go. So I would go ahead, 5/3 multiply by all of that. I'm going to get something like 1.306. So that is my mean squared treatment. So then I would want to know the mean square error here. So mean square error, it's sum of, and I'm going to add over the groups there. So n total minus the number of groups. So there are 20 observations total minus 4 groups, and then it'll be 5 minus 1 for all groups. Times SI squared. So you're going to get 4/16 times 0.155 plus now I'm looking here, 127 plus 0.092 plus 0.058. Well, I should probably have a square bracket. So then I'll end up getting like 0.108. So my mean square error here is 0.108. Ultimately, what we're going to end up doing is we're going to look at the, we'll end up looking at the ratio specifically of the mean square treatment. So this is the differences between groups and the mean square error. So this is within. The idea is if the mean square treatment is a lot bigger than the mean square error, then knowing what group an observation is in gives us a lot more information. So it indicates that probably at least one group mean is going to be different. So that is setting us up for the test that we'll be running. So we want to do this when we want to test if the averages are different, the population averages are different for two or more populations. A lot of times we'll say more than two populations. You could use it for two. It's not typical. If you have two populations, you're going to look at a two-sample t-test. So conditions, you're going to see that we want to have representative sample. Absolutely, usually the easiest way to do that is to have a random sample. We want to know that our sample sizes will be large enough that we could count on the central limit theorem to kick in for the sampling distributions of x bar 1, x bar 2, x bar 3, and x bar 4, because we have 4 populations here. We want to know that the two groups, the two populations are independent from one another. You can't have an observation in one group that's also going to be in the other. They have to be totally independent groups. And then one thing that we're looking at too is the population variances are equal. And we will have a rule of thumb that we use to look at if they're close enough, and we will go through that. So definitely just keep an eye on this. If the spread of one of your samples is really, really different from another one, this condition can be a concern. So once you have those met, the null and alternative hypotheses, they will look a tiny bit different than before. So our null is going to be, they are all equal to each other. So the mean of the 300 degree treatment group is equal to the mean of the 400 treatment group, is the mean equal to the mean of the 500, is equal to the mean of the 600 degrees Celsius treatment group. You just assume by default, if nothing interesting is happening, they're all equal to each other. The alternative is at least one's different, so at least two of them are different from each other. So at least one differs. So from there, we are now going to use an F statistic. So in the prior weeks, we had a Z test statistic, which meant that we used a Z table or R to get our, we had a Z statistic, and then we used that to get our p-value. Last week, we used a T test statistic, and then we used like a T table or R, looked at the probabilities from a T distribution. An F statistic means we're going to introduce an F distribution. And the way you calculate that, it's going to be the mean square treatment over mean square error. And we're going to go into, so sum of squares treatment divided by your number of groups minus 1 over your sum of squares error over your total sample size minus the number of groups. So the F distribution, it's really usually a very skewed distribution. It's a right skewed. And whenever we look at the p-value, we only look at the upper tail probability. That's the only probability that we ever really use from the F distribution here. And so like the T distribution last week, it had degrees of freedom. F distribution has two sets. So it has a numerator degree of freedom, which is number of groups minus 1, and it has a denominator. So numerator degrees of freedom, denominator degrees of freedom, which is your total sample size minus the number of groups. And whenever anybody talks about oh, I have an F statistic of 4 with 3 and 2 degrees of freedom. If they don't specify which is which, we always say the numerator degree of freedom first and then the denominator degree of freedom. Although it is helpful to just label them. It really takes out that ambiguity there. And so the larger your F statistic, the further out in the tail you go, which means the smaller your p-value is. So the bigger your F statistic gets, the stronger evidence you find that at least one of the population means is different than the other. And if you think about it, it basically means that, hey, at least one of those sample means is really wildly different than the overall mean. That's what it kind of is getting at there. So F distribution, it's going to be positively or right skewed. It goes from 0 to infinity. It's not going to be a negative value. And it has 2 degrees of freedom, so it has your numerator degrees of freedom, new 1, and then it has your denominator degrees of freedom, which is new 2. And so we do have a tendency to write, oh, I have an F statistic with whatever your numerator degrees of freedom are, and then your denominator degrees of freedom. So as your degrees of freedom get larger and larger, see, it goes from this green one that looks almost like an exponential to getting more and more more symmetric shapes, more bell-shaped. And it is a ratio of chi-square distributions. We're not going to necessarily use that information too much, but know that a lot of these distributions we use are very related to one another. There are definitely special cases of the F distributions that are T distributions and so on, that kind of thing. So here, oops, I used G before for groups, but WebAssign will use I. So for a single factor ANOVA test, the p-value is always the area to the right, and it'll be with an F statistic, number of groups minus 1, your total overall sample size minus number of groups. And here's some example code. We have more included at the very back of these notes. So things to note, so here's an F statistic, here's your numerator degrees of freedom, denominator degrees of freedom, and then I like to use this lower tail equals false because it tells it to give me the area of the upper tail. If you put T, capital T for true, it'll give you the lower tail, which we don't want. Not here anyway. So returning to our carbon materials and at 4 different temperatures, we're going to go ahead and run this F test to see, hey, is the average of at least one of these treatments different? So wording it, does the mean pore size of carbon materials differ for at least one of the temperature treatments? 300 degrees Celsius, 400 degrees Celsius, 500 degrees Celsius, or 600 degrees Celsius. I find this useful to include what they are, then I know at least how many groups there are. Because if I left this out, it is not really clear. At least I would put at least one of the 4 temperature treatments. But it's useful to know what they are. So from there, we're going to go ahead and check conditions. So the experimenters, they went ahead, they took 5 specimens from each temperature. The specimens are randomly sampled for pore size. Populations are assumed to be normal. Thank goodness, because we only took 5 for each temperature. So that's 5 is a very small sample size. It is very useful that we can assume normality here. Then we want to test to see if at least one mean is different. So are the samples random and representative? Yes. So no, you can be representative and not be random. And you can be random and hopefully you're representative always. Just know that you can be representative and not random. It's not very, very easy. Or you can be random and that usually will guarantee you're also representative. So based on central limit theorem, can we know that the sample size is so N1, actually I'm going to do this, N300 is equal to N400 is equal to N500 is equal to N600. So for subscripts, I feel like it's extremely useful to use useful subscripts where you can. If you use N1 and N2, you need to tell us what 1 and 2 are. If you use numerical labels like that don't make it really obvious which groups, you need to label them. So is equal to 5. And 5 is big enough because populations are normal. So J equals 5 is big enough. So then, are the populations independent? So just a moment here. Okay, so then condition 3, are the populations independent? Yes, so any observation here is going to be in the 300 group, but not also the 500, or the 400 group, but not also the 600. None of the materials are going to be in both, so yes. And then are the population variances approximately equal? We will check on this. We'll comment check because we're not sure. We definitely don't want the variability of one group to be a lot more than the others, or one of them to be a lot smaller. So we definitely have rule of thumb that we use. In general, whatever your biggest sample variance is over your smallest sample variance, I'm going to use a different letter, as long as it's less than 2, well, actually the variance is less than 4, you should be okay. So as long as you don't have a sample standard deviation that's at least twice as big as another standard deviation, you're okay. That's our rule of thumb there. And we will go through that in another example. I just don't think we explicitly go through it here. So then my hypotheses here, I'm going to use, so we are still dealing with means because what we're measuring is quantitative. Pore size is quantitative. So I'm going to use subscripts 300, 400, 500, 600. You can use whatever you want, but if it needs to be very clear exactly which subscript goes with which group. So because I use 300, 400, 500, that's okay. But if I use 1, 2, 3, and 4, I would need to tell people what 1, 2, and 3, and 4 stand for. And then this is where this changes up just a little bit. It does not mean that they're all different, just at least one. Because if I made the statement, all of them are equal, in order for that statement to not be true, just one of them has to be different. Right? They don't all have to be different, just one of them has to be different. So at least one is different. So at least one mu I differs. So if at least one mean for one of those populations differs from the others, that's enough to discount the claim that they're all equal. So calculating my test statistic, am I getting my p-value here? Might kind of have a giveaway here. So my mean square treatment was at 1.306. My mean square error is at 0.108. So my F statistic is just the ratio of that. Ideally, hopefully, if you're lucky, your mean square treatment is bigger than your mean square error. If it's not, you're probably not going to find very strong evidence that there at least one mean's different. So 1.306 divided by 0.108, I get something like, I don't have this written here, 12.093. So I have an F statistic of 12.093 on numerator degrees of freedom of 3, denominator degrees of freedom 16. So this is number of groups minus 1, so that's 4 minus 1 is 3. This is n total, so there were 20 total observations minus number of groups, and that's going to be 20 minus 4 is 16. That's where those numbers come from. So throw it into R. There are F tables, and if you really, really want practice, like reading an F table, by all means, it's going to be similar to the T table in the sense that your p-value is going to be between two values most of the time. It's going to be an interval if you use the F table. It's also a really old school skill. Now that computing's become really big, people are doing that kind of thing by hand a lot less. It doesn't impress people quite as much to bring out those. And we used to have them in textbooks. They were these big old fold out tables, and people just don't like them anymore. I can read them, and I can show you all how to read them if you really want. Hit me up if you do. Just know it's a little bit of a dated skill. So when we throw it in, so PF, so before we did P norm, then we did PT, now we do PF. Hopefully you see the pattern there. You get a p-value of 0.0002 and some change. It's a pretty small p-value. So my F statistic was 12.093. I'm going to put numerator degrees of freedom. It should be right there after that. 3, denominator degrees of freedom is 16. My p-value, what was it? It was equal to 0.0002. As long as you go at least 4 places, we're pretty happy. Definitely never round fewer than 2. We're usually going to be pretty unhappy if you round fewer than 2 decimal places. It's just not as useful. You're much more likely to make rounding errors that way. So here I have a very small p-value. It's smaller than my significance level. This means, you know what, it's super unlikely we would have observed what we did in our samples if the means of the populations were really the same. So we're going to reject that they are the same. We're going to go ahead and conclude at least one population mean differs from the others. So here, there is very strong evidence that the mean pore size of carbon materials differs for at least one of the temperature treatments. And I'm just going to list them again. 300 degrees Celsius, 400 degrees Celsius, pretty warm. I believe 100 degrees Celsius is boiling. It's definitely warmer than I ever want to experience. There we go. So we reject the null hypothesis at the 0.05 significance level. I like to stick the p-value with information about its statistics. So with an F statistic of 12.093 on 3 and 16 degrees of freedom with a p-value of 0.0002. I always forget how many zeros I've said. And then we would say, yes, there's very strong or convincing evidence that the mean pore size of carbon materials differs for at least one of the temperature treatments. And that's where it would be from there. So that's one example. We're going to go ahead and investigate more about sum of squares in lesson 32. And we'll have another example in 33.